All right, I think we're going to get started here. Can everyone hear me okay? Good. Welcome. Thank you, everyone, for coming. This is our 5th year doing this so far. How many of you, whose first time is it here? Show of hands. Wow, that's awesome. How about second year? You? 3? 4? Wow, okay. 5. All right. Yeah, so first off, I want to thank our sponsors, thank all the attendees that are here that help us pay for this, put this on. We'll have lunch around 12, and then later on we have a small after party. We bring in a bartender and everyone can hang out and have drinks, whatever. Yeah, I think we are probably ready to bring up Lane, our first speaker. We do have lightning talks also, sorry, almost missed that. If you'd like to sign up to do a lightning talk, you can access it on gowestconf.com or I believe scan this QR code and get that. Yeah, so an hour total of lightning talks and we'll try and fit as many as we can in there. So yeah, I think we'll go to Lane.
Hello? Is the mic working? Hello? Yeah. I can just talk loudly. It worked? Okay, cool. I am wired. That cold brew has so much caffeine. I'm not actually that nervous, but I am definitely a little jittery. Are we able to see my screen okay? Zoom it in a bit. I'm not doing slides because I struggle with slides. So I wrote this talk up as a blog post. I was chatting with Mariah about what I should talk about. And it turns out I don't have very many interesting things to say about Go, which is problematic at a Go conference. But what I do have is a lot of data. So we're going to jump into a lot of data. For those of you who don't know me, which is probably most of you, my name's Lane. I'm the founder of Boot.dev. We teach backend development in Python and Go. So I thought it would be fun to kind of go over a lot of our students' stats and talk about, like, where people struggle in learning to code, but I'll try to tie it more into the Go programming language because I know that's what we're really here for today. So before I actually jump into that part of the blog post, let me just show you what I mean by, we teach backend development in Python and Go so that all the data kind of makes sense. So this is the curriculum for which we will be looking at data today. We teach people who are just getting started to learn to code Python first, and they take all of these kind of intro to coding courses and computer science courses in Python. And then right here in course number 14, by the way, is that big enough? A little bigger? Is that a little better? Cool. It's right here in course 14 is where they learn Go for the first time, after all of these kind of core computer science basics. And then we teach backend specific stuff in Go, where you're like building a RESTful API with Postgres and SQL and that kind of stuff. And then there's 23 courses in total. So that should hopefully give you a little bit of context as we go over some of these numbers. And then also, again, just so you kind of understand the statistical significance or lack thereof in some of these numbers that I'll be sharing. We have 336,000 roughly registered students on BootDev. And about 18,000 paying members who are actually committed and going through the program in a more serious way, I suppose. Registered users are able to read all of the content. All of the content's free to read, but they're not really doing it in the interactive way. So really, the sample size should be closer to about 20,000. There's 2,100 lessons-ish total on the platform. Granted, I wrote this blog post about a week ago, so it's changed a little bit. And 217 total chapters, 21 courses, 9 projects. So on that page I was showing you, we're kind of mixing the idea of courses and projects. We try to teach new concepts in courses and then use projects and guided projects as kind of a way to reinforce the learning that happens in the courses. This one's pretty interesting. So over the full lifespan of boot dev, which has been about 3 years, there have been 10 million, roughly, lesson completions. So this is people actually like writing code for an assignment, submitting it, getting it correct, and about 64,000 course completions. This graph here is, the blue bars represents lesson completions by month. So we've got October of 2023 through September of 2024. And then the orange line is just our active members. Okay, so let's talk about some content finally. One of the things that I thought would be most interesting is what are the hardest things to learn when learning to code? And luckily we have some data on that now, which has been pretty interesting. So we'll start here with Python. I know I didn't know I'd be the first talk. This is like so awkward at a Go conference, and here we are talking about Python. So these are the first 10 chapters post paywall on boot dev. So chapters 4 through 14 of our Python course. So this is like someone who's just getting started learning to code, knows very little about code. These are the first 14 chapters that they're going to encounter. And the reason it's interesting to break it down by chapter is because we try to separate chapters based on concepts. And these represent the drop-off points, right? So first bar is just everyone that did a lesson in the 4th chapter. And again, I chose the 4th chapter because the first 3 are completely free, so there's like a weird drop-off that kind of skews the data after chapter 3. But so, you take 100% of people that have completed the 1st chapter, a decent number of them get to chapter 2, and they kind of fall off as the course progresses. And chapters 7, 8, and 9 have the biggest drop-off rates. And so you could say that chapters 7, 8, and 9 probably demotivate people the most. And those are the chapters that represent comparison operators, loops, and lists. And lists is really the terrible one with a 15% drop-off. Finally, for Go developers, so there's really 2 entry points on boot dev. People who are just getting started learning to code, like I said, start with Python. But we actually do have a lot of people kind of joining the platform and starting in the Go section because they're not new to programming or computer science. And so those are kind of like, it's not quite true to say that those are the 2 most popular courses, but they're definitely the 2 most popular entry points on the platform. And Go has a very different look when you look at how people are dropping off. There are a few chapters with much higher drop-off rates, which is kind of interesting. Like I said, the biggest drop-off rate in the Python course had, what, 15%? A 15% dropout rate. In Go, chapters 4, so be right here, 5 and 8 have the biggest drop-off rates. And that's structs, interfaces, and slices. Which really surprised me. Like, as I was putting all this data together, I really expected channels to be where people give up. It's like the one thing in Go that's like even kind of hard. But it didn't show up in the data. So then I was like, okay, well, maybe giving up actually isn't all that correlated with how hard a concept is. Like, maybe there's a bunch of other stuff that goes into that. Conveniently, we measure a difficulty score on boot dev. And this is kind of how it's one of the things we use when we're updating our content. So we don't have all that much content on boot dev. I mean, it is 2,000 lessons, but like it's not It's not that much. I don't know. We get like 100 to 150 reports per day on our lessons by students, and so we're like always updating them. And this difficulty score, which Alan wrote, by the way, sitting right there in the white shirt, is kind of how we know if a lesson like actually is hard, because you'll get some really weird reports from students about like what's hard and what's not. So it's really helped us quantify it. But let me talk for a second about what goes into a difficulty score. So because all of our lessons are pass-fail, we have a few different things that can go into the score. We've got the number of attempts you submit before you actually pass, right? So like you sit there and fail 5 times and then you finally pass. That goes into the score. We've weighted it, 4 out of 10. The number of times the student views the solution, and I actually think this one's calculated on like the number of students who view the solution before completing the assignment successfully. And then we also have this AI assistant. You can basically think of it as an amazing, if any investors are listening, it's the best chat GPT wrapper you've ever seen. We've prompt engineered the hell out of it. Very expensive technology. We look at how often people chat with that bot before getting the answer correct, and that also goes into the score. By the way, I should have asked before I started, when do I go to? Cool. I'm already 14 minutes in, so we're in trouble. I'll go faster. All right. Point is, we calculate this difficulty score. Got it. So I potentially have you people for another 30 minutes. Great. Sorry about that. Cool. So we calculate this difficulty score for all the lessons. And then what I did here was average the difficulty score on a per chapter basis. And the results are a little bit different. Loops, which I believe, loops didn't even show up in these drop-off rates either. Loops and channels, right? Now it's starting to look a little bit more like what I would expect. Loops and channels were the most difficult chapters for people in the Go course, followed by maps, slices, and functions. Now there's a few problems here. This talk is kind of my ramblings through digging through our own database for interesting things. After I looked at this, I realized that taking the average of the difficulty scores might not be the best way to find the actual difficulty of a chapter. Because if you have a long chapter with like 2 of, say, the hardest lessons in it, but then it's getting watered down by all these easy lessons, like the easy lessons don't make the chapter any easier. They make it longer, but they don't really make it any easier, right? So I changed it a little bit. And in this graph, I took the number of most difficult lessons, right? So essentially in these chapters, how many hard things am I asking the student to learn? And when I sorted this way, now, haha, channels are the hardest. So I've sort of backed my way into the answer that I wanted, which is a great way to do research. So that's great. I still wasn't quite satisfied. So the last thing I did here, I can't remember, so I'm going to read my own blog post for a second. All right, I was thinking, this is weird. Like, I'm just doing a cutoff at like difficulty of 6 and then only summing like the most difficult things. That doesn't feel right as an engineer. Like, I should be doing some kind of, weighted sum. And I definitely wasn't satisfied with the way that I was sorting everything. But when I tried just summing all the difficulty scores, it gets weird because more weight is given to these lessons that are not quite as difficult, right? 3 3s is not as hard as 1 9. So I think the right thing to do, had I been given more time, would probably do some sort of exponential scaling, so that the more difficult lessons get some sort of higher weight than just a naked sum. But all this to say, channels are hard. Channels are hard. Cool. Now this isn't so Go specific, but I thought this would be interesting. Just in general, I used this same calculation with kind of the cutoff, and we're looking at which chapters have the most hard concepts generally, and sorted all the chapters on the whole platform. So it's 217 chapters. And surprisingly, loops in Python came out to be the hardest. And I think it's important to like note that it's a measure of relative difficulty based on where the student is, right? So I think it can kind of be hard if you've been coding for a while to remember that like it actually is pretty hard to learn loops and lists like in that very first programming language. And I mean, the other thing that's interesting to consider is like, this isn't like a perfect measure, of course, of how difficult these concepts are, like fundamentally, because it's also based on our content, right? So we may have written this chapter poorly, or maybe this chapter, we just added more challenges to it. But it is noteworthy to say, I mean, we've spent the most time optimizing this course, especially for, you know, to smooth out the difficulty curves, because this is the first course in the platform, and yet it's still the hardest thing. So that's pretty interesting. And Go's channels chapter is like all the way down like 12th place on the platform. So really most of the difficulty lies, at least for our students, in the just learning coding and computer science basics stuff. Okay, so that's all the chapters. That's all of them. By the way, if you want to follow along, this is just a public blog post on blog.boot.dev. It's the first entry. So if you wanted to skim through the data, you're welcome to. Okay, then I aggregated all the data by course, because it's really hard to read that 217 entry table. But when you look at all of our courses, functional programming is the hardest. Should be, I mean, people, if you ever talk to a functional programmer, then they'll tell you about how easy it is. And I just, you know, I have the data. It's really not like I'm a big fan of certain things in functional programming. That's why we teach it. Like I think, you know, recursion, pure functions, super important concepts. But I don't care like what your, you know, Haskell professor with a PhD in mathematics says. I don't think it's actually that easy. So functional programming data structures coming in really difficult. But it was noteworthy to me that the Go course, just the basic Go course for developers, came in with a higher difficulty score overall, quite a bit higher than Python. So in other words, it seems like Python has some more difficulty spikes, right? Like it had that list chapter that was really hard. But overall, the Go course, for whatever reason, was a little bit harder. Granted, these scores are interesting. I mean, functional programming is really hard. It's like twice as hard as the Go course. So again, mathematics professors. So we do have a few problems here, and this is really for any readers that are really looking at this bottom half of the graph. The problem is that some of these courses, like Git and Git2, shells and terminals, they're completed on your local machine, and we have like a CLI tool that we use to like make sure that you're doing the things, you know, getting everything into the correct state. Difficulty score doesn't really work for them. So like you mostly have to ignore that part of the graph at the moment. And the big problem is just that some of the metrics that go into the difficulty score, like how many times you submit before getting it right, don't really work on these types of assignments because you're basically guaranteed to get it right the first time because you're able to check against your own stuff, which isn't really the case for these one-shot, like write the function correctly types of lessons. So what we are planning to do that we haven't gotten to yet is add a metric to the difficulty score that's basically how long it took you to do the lesson, which means we'll have to like start timing you when you start doing the lesson, just like whole thing. But that should help. That should help figure out some of these at the moment kind of unbeknownst difficulty scores. Okay, wouldn't be a talk in 2024 without a little bit of AI. So we've got a chat GPT wrapper. Again, if anyone's looking at acquiring boot dev for north of $1 billion, it's much more than that. But we'll just pretend that it's not. The way that the AI tutor works and the way solutions work on the platform is if you want to view a solution before you complete the lesson, you actually have to pay in-game currency. It's a very gamified platform. You have to pay gems. It's not a microtransaction thing. It's not that. But like you earn gems along the way, and then you use them. And if you don't have any gems, then you lose XP for that lesson. So you won't gain as much experience points. Same with AI Tutor. The AI Tutor is cheaper than viewing a lesson. So we want students to chat with the bot, who has been, again, very carefully prompt engineered to not give you the answer, and instead to kind of teach you in like a Socratic way. Like he'll sit there and like pester you with annoying questions about why you wrote your code a certain way. So we try to push people to that. So this graph is the total number of messages sent to Boots, our AI chatbot, and the total number of solutions viewed. And it was interesting to see that people chat with the AI bot about 50% more than they view solutions. Now, if we aggregate that by count per user average, then boot chats are actually 3 to 4 times more common than viewing solutions. And this actually really confused me because it didn't make sense to me why that disparity would be so great just when you start going on a per user basis. But I think what PostHog was doing, which is what we use for kind of product analytics, is excluding all the zeros. So it's like when you chat with Boots, it seems that you have a longer interaction with him than you would if you were just like toggling the solution on and off, right? So you sit there and chat with him for like 4 or 5 or 6 messages. This one was really weird to me. I really didn't expect the graph to shake out this way. So you can do these things before or after you get the lesson correct. If you chat with Boots or view the solution before you get the lesson correct, it costs you these things. It costs you gems or costs you XP. But it's free to do it after you get the lesson correct. So you can like review the instructor's code for free. We want you to do that. And again, you can ask follow-up questions to Boots after you get the lesson correct. Interestingly, the graphs, like they're different. So Boots after submit. Okay, so Boots before submit is the most common thing. But solution before submit is actually quite rare. Like people look at the solution a lot after they get the lesson correct. In other words, like people don't like cheating is kind of like what this graph says to me. Like people really don't like cheating. People like viewing the solution, but only after they've already got it correct so that they can review against the instructor's code, essentially. But the AI chatbot is disproportionately popular before you get the answer correct. Solutions are disproportionately popular after you've already got it correct. And then, again, we're at a Go conference. Really awkward. This is the first talk, and it's not just completely about the Go programming language. But I did break it down by language. And I expected it to be pretty similar across language, but it wasn't. In the Python course, Boots and solutions, pretty 50-50. 9% of people used Boots, 9% of people viewed solutions directly. In the Go course, solutions were more popular. I don't know, Go developers don't like AI. Like, solid 2.5% disparity there. But now when we look at the hardest Python course, which is functional programming, and the hardest Go course, which is HTTP servers, that's the one where you like actually build a web server with like Postgres and it's a CRUD app and things like that. Changes a lot. As the courses get harder, the amount that students prefer the AI chatbot over viewing the solution goes way up. I mean, both numbers went up in absolute terms, but people really were sitting there and chatting with the AI bot to try to figure out, why things are a certain way. And interestingly, HTTP servers, which at least by our difficulty metrics is not harder in absolute terms than learn functional programming, actually did have even more Boots usage than the functional programming course. I do have one suspicion here. I think it's because the web servers course has like much larger steps. So you like build an entire endpoint in Go, like hook it up to a database. Like you've got to do all these things. It's not just like write one function. So it would make sense to me that you have to sit there and chat with the AI bot over and over and over to get through a single step. And then I broke it down by model. So, am I doing on time? Boots is powered by 2 different models, powered by AI. Claude Sonnet, GPT-4o. So these are the two kind of flagship models for coding. Claude is Anthropic's model. It's specifically kind of designed to be good at coding, whereas GPT-4o is a little bit more of a general language model. And the interesting thing is I ran this query like 2 months ago, and GPT-4o was winning by like a decent margin. Like it was like 50% better performance. And the way we're calculating performance here is as students chat with the AI bot, they can like thumbs up, thumbs down the messages that come back. It's like if they're useful or not. So pretty early into the experiment, it seemed like 4o was way more popular, but now it's really changed quite a bit. And can't remember if I mentioned this already, but we split the chats 50-50. So it's like every time you chat with Boots, you randomly get assigned Claude or 4o. And Claude has a higher like count and a lower dislike count at the moment. So it's coming out ahead. We were initially thinking that 4o would be better because supposedly it's a more general purpose language model, and what you do with Boots is not generate code, which is what supposedly Claude's supposed to be good at, is like helping you as an experienced developer just like generate functions on the fly. And basically our hypothesis was 4o would be better because what you're doing with Boots is not that. You're sitting there asking for help and you're getting help back in natural language. But we need more data. I don't know if you noticed, these are tiny numbers. Like the total messages here is 360,000. We only got like 1,000 likes and dislikes. So I think we need to update our UI to encourage using the thumbs up and thumbs down a little bit more. So AI content help. So this is us using, this has nothing to do with Boots anymore, the AI mentor. This is like us using AI to generate content. We've experimented with a lot over the last couple of years, basically since GPT-4 came out. And it's mostly a terrible, terrible idea. Like we have been able to use basically nothing that's generated with 4 or 4.0. Like we like the content to be interesting and human and have good examples, and all you get is like really generic, bland stuff has been our experience. And we've tried a lot. We've written a lot of scripts. We've tried like bloating the context window, giving it tons of examples of our current content. We've tried using the fine-tuning API. Maybe we're just bad AI engineers, but it hasn't been working. But we have found a few other use cases that might be interesting. So the first is, I think I mentioned earlier on, students report issues on lessons all the time. This is like, I think this is one of, I'm really glad that we did this early on. We've got a little report issue button on every single lesson in the app. And if a student's having any sort of trouble, they'll report an issue. And we get like 100 of these a day. And we're only a team of 5 engineers. So it's a lot of work to deal with these tickets. I actually think I have the stats here. So we've closed 10,964 of those. And at the moment, we only have 73 open. So we try to get them closed like literally every single day. And what we found is that these reports fall into basically 5 different categories. Student error. So the student's just like wrong about whatever they're reporting. Happens a lot. We've got enhancement. So the students suggesting a change that they think would make the lesson better. And it's essentially, it's valid in some way, and maybe we should. Obviously, a lot of these are opinion-based. It's like, I wish this wording was slightly different, but that's one category. Bug, the students found like a valid bug in either the solution code or just the assignment like description in general, like maybe we're telling them to do X, but really they should be doing Y. Bad change, so the students identified a bug that's not real, due to their own code. Or diagnose question, which is just the students asking a question, and we don't want them to ask questions there because we don't respond to these tickets. We just like deal with them. So we want to like push them over to our Discord or somewhere else where they can get help. So of these 5 types, only enhancement and bug are actually actionable by us. Everything else we basically read and close. So we started using GPT-4o. Do you remember, Hunter? 4o? Yeah, 4o. We started using 4o specifically to diagnose these. And it's been awesome because our little bot opens GitHub issues, and now we just tag them with these 5 with these 5 labels. And it's much easier for us now to, when we look at a ticket, which has been aggregated by lessons, so we've got like maybe 5 reports on the same lesson, we can already see what the AI has diagnosed the ticket as. We've been manually curating that for a while, to the point where now, if it's still diagnosed, like diagnosis question after 3 reports, we just close it. Like the AI bot just closes it, because there's enough data there that we're fairly confident there's not a problem here. If there is a real problem, it'll probably get reported again. So that saved us a lot of time. This is also interesting, just the total counts of different types of reports. You'll notice these are very small numbers. That's because we only started having the bot actually take action on these like a week ago. So I probably should have ran it again today to have slightly higher counts. But at least so far, it was interesting to kind of see the breakdown there. Okay, the other use case that we found for AI is intentionally making content worse. Seems like a weird use case, but I'll spoil a bit, a new feature that we're working on at the moment. We're working on something that we're calling spellbooks internally. It's a feature that is meant to deal with issues that students have reported surrounding, they want to take notes, they want to bookmark earlier lessons, they want like quick access to documentation. And the feature that we've come up with, again, that we're calling spellbooks, is basically like a fuzzy search bar where you can type a concept that you've already learned. So as you're going through the lessons, you're unlocking spellbook pages, which you can basically think of as like encyclopedia entries for individual terms. So if you're in the Python course and you're working on lists and you forgot the syntax for loop, you start typing loop, you get this spellbook entry for loops. And the idea is it's a very condensed explanation with just like a few examples and maybe link to documentation about that concept, which would be a nightmare to generate by hand. There's only 5 of us, we've got 2,000 lessons. Like we really didn't want to write all of these spellbook entries. It's also just really dull content. I don't like writing dull content. AI is good at this. So we give it our existing lesson on loops, which is like large, with very human examples. It's written in a way that's supposed to be interesting. It takes us a long time to generate that content. We can take that, we can make it intentionally boring and succinct with AI. So it's transforming something that was actually hard for us to make into something that's easier, but in a different format. And that's worked really well. There's still some human curation. Like we wrote a script that basically takes an entire chapter of lessons and generates the spellbook entries. We still have to read over them, make sure they're good, make sure nothing got messed up, but it saves a lot of time. Let's go on time. I'm going to try to finish up and then questions. Okay, cool. I'm almost done. Just a couple more stats that I thought were interesting. That's all we got left. So resetting lessons. After a student successfully finishes a lesson, they can reset it and they can try it again. 12% of lessons get reset. Like people really like to do the same content over again. This blew me away. And we see it really on a course basis. So people like do the whole Python course. It's like 160 lessons. They'll be like, that was great. I don't remember anything. And they'll reset the whole thing and do it all again, just to practice all of the coding challenges again. So we were surprised. Like we knew people wanted resets. We've been asked for this all the time. We finally implemented it. I was very surprised by the usage. People like to RTFM. This one kind of surprised me as well. We have an audio feature, again, powered by AI. Any acquirers listening? It's just ChatGPT's thing that like reads the content text to speech, right? So you can listen to the lesson explanations, which are usually about 3 or 4 paragraphs instead of reading, and people don't use it. It's like really easy to use. It's right at the top there. You just like do the drop down, press play. People like to read. People listen to the content like 1.4% of the time. They'd much rather read it, which I thought was interesting. And like, I mean, I didn't write this thing, but I think the text-to-speech is pretty good. It's the same one you get on the ChatGPT UI. Like it works pretty well even on code. But yeah, people just don't really listen. Vim mode, 7%. 7% of people use Vim. This blew me away. So our in-browser editor has Vim bindings, and you go into your settings, you turn it on. There's literally, hey, there are hundreds of people using Vim mode. Uh, and especially considering, we do have a lot of experienced developers that join and take our Go track specifically, but like these numbers are muddied by like a lot of people getting into coding for the first time. They don't even know what Vim is. So they usually start with Go. That's not always true. Prime has grown a lot in the last year. I don't know if you've noticed. The Prime engine's gotten really popular. And so he does have more of a beginner skew to his audience now than he used to, I think, when we first started working with him about 18 months ago. That's it. That's the whole thing. Thanks for listening. If anyone has any questions, I will do my best to answer them. You can ask me anything, but I mean, I did just spend a lot of time digging through the database, so I have some numbers in my head. Yes. All right, who was it? Todd? Just look that one up. I don't know. I don't know. Yeah. That's a really good question. So the way it's implemented in the UI is you can reset on an individual lesson level, or you can back out and reset all the lessons in a course. I didn't split that data. I could go do that. Anecdotally, I would have to guess the majority of this is resetting entire courses, just because that's what people talk about the most in our Discord. We're like really active in our Discord and talk to a lot of people. So I think that's the case. Yes, here first.
So I noticed places that lists tend to be for students.
Yeah.
Somebody who's been programming for a long time. Why are those hard? So that's very interesting to me because those seem very intuitive.
Yeah.
Do you have a sense of like why that tends to be hard for new programmers?
Yeah, loops and lists. I think so. So like I said, we get a lot of people in the Discord asking questions, and loops and lists and slices and go are a big one. I think it's disproportionately difficult in the Python course because it's people learning that concept of iteration for the first time. It's like chapter 7, I think, or 8 in our Python course, and up to that point, you have no concept of like your code running multiple times, right? You write a line of code or a bunch of lines of code and it executes kind of top to bottom. I think it's the first time students have to wrap their head around like, I have to think about the state of my program as something more than just which line I'm on, like in a top to bottom execution. It's like these 4 lines are executing a bunch of times, and the variables can be different things, like every time I'm on a different line, right? I think that's where the biggest disconnect is. Yeah. Yeah. So in this like consistent ticket squashing effort, every day we get all these reports and we're constantly kind of trying to deal with them. We tag the difficulty score of the lesson on the report as well. So like there's a bunch of things get tagged, but we're looking at like, all the reports on the lesson, the current difficulty score. And that's basically been an ongoing effort. That doesn't help solve the problem of like an entire chapter typically. I just finished redoing our entire data structures course, like going through it lesson by lesson. This was like just an effort I had a couple weeks ago. It took like a whole week. So I guess the question is just like blood, sweat, and tears. Like you just got to get to the different difficult parts, in turn and make changes. So. Yeah. 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 That's true. I totally forgot about that. You've been listening to too much TJ DeVries. He's really on a quest to get everyone to believe that one-based indexing is. Yeah, I think that's true. I think that's true. Yeah. Let's see. Sorry, here and then yeah. Interestingly, no. Our like average age is like 30, 31. So to give like an idea of where people coming to BootDev come from. So we work a lot with the Primogen, if anyone's heard of him. Also TJ DeVries. They tend to bring in a more experienced audience. A lot of people that are again starting in like the Go course, the SQL course, some of the more advanced stuff. And then we also do a lot of marketing with gamers. But what we found is like Fortnite doesn't work. Fortnite gamers don't want to learn to code. But WoW gamers, World of Warcraft, and old school RuneScape players really do. And they tend to be like, 31, 32 years old. So actually, it does skew older, but those audiences also do skew like new to programming, not new to computers, right? So they've been gaming for 15 years, very familiar with like installing mods and stuff like that, but pretty new to coding. Yes. Warhammer, Magic the Gathering, yeah, those work well for us. We just, anything that like me, Alan, and Hunter actually play in our lives, we just like contact those creators. That works pretty well. 2 more? Okay. Yeah, so by the numbers, I should have included this graph. About 40% of people that join BootDev are brand new. So they like never seriously tried coding before. Wait, no, sorry, I mixed that up. That's 25%. Roughly 40 to 50% of people have been coding for, as they self-describe, about 3 months and have been like struggling to learn. So they're like, jumping around from YouTube tutorial to YouTube tutorial, probably not following anything too structured in terms of curriculum. That's our biggest audience. So people that are like somewhat interested in code, but have like never had a coding job. That's the lion's share. And then another like 25 to 30% of people who are self-described as like mid to senior level developers that just want to learn Go and like learn Go best practices. I got one more. Yeah, talk to me after, yeah. No, but there is a really great clip of Asmongold reacting to a Bellular video that we sponsored where he goes, so they sell shoes? No, so. All right, thanks everybody.
Thank you, Lane. All right, we're going to take a small break and we're going to come back at 11 with Adam. It's going to talk about profiling. It's going to be awesome. The restrooms are all the way to the lobby to the left on the right side. I don't know. All right, let's take our seats and get started here in just a minute. Awesome. All right, let's go ahead and get started here. We are very excited to have Adam to present for us today. He is a software engineer at Google. You work on Prometheus, right? Google Cloud Managed Service for Prometheus. That's a lot of words.
We'll get into that.
We'll get into it. Awesome. We're very excited to hear from him, and we'll hand it off to him to get started. Thank you.
All right. Well, this is not an introductory topic for most people, but hopefully y'all will be with me as we go. So welcome to Continuous Profiling for Scale. My name's Adam Bernot. I'm a software engineer at Google Cloud, and I work on the Google Cloud Managed Service for Prometheus. Also, a shout out to Adib, who is my summer intern, who worked on our continuous profiling solution for his internship project. Today, I would like to cover some backgrounds on the problems that we were trying to solve that led us to continuous profiling. I'm going to discuss a little bit about the basics of continuous profiling, what it is and how it works. And then I hope to spend the majority of the time talking about how we designed and implemented our solution and some lessons learned and future directions for us. And all right, so you may or may not be familiar with the Google Cloud Managed Service for Prometheus. I will probably refer to it as GMP. But GMP is a solution for collecting metrics, and it's part of the Google Cloud Observability tools. Oh. We were on my slide a little. Did I open another window?
Yeah, that's in presenter. Oh, is it in?
Oh. That's fun.
There you go.
Cool.
Thank you.
That's better. All right. So yes, GMP is a solution for collecting metrics with Prometheus, and it's one of the Google Cloud Observability tools. It's enabled by default on Google Kubernetes Engine, making it easily accessible to Google Cloud customers. However, it is open source software that can be installed and deployed just about anywhere that Prometheus metrics need to be scraped. And our operator is designed to run in any Kubernetes cluster. GMP itself runs in many thousands of Kubernetes clusters and collects trillions of samples. So with that context in mind, our customers care about efficiency because GMP runs on their nodes. So every megabyte of memory that we use to collect metrics is a megabyte that's no longer available for them to run their workloads that are executing their business logic. And likewise, anytime that the CPU is working on collecting metrics, it's not executing their business logic. Customers accept this trade-off because those metrics provide value, but none of them will be mad if we accomplish the same task with a reduced footprint in their cluster. In addition, we also care about efficiency because of our scale. So consuming a bit less memory in each instance may scale to terabytes of memory over the fleet, and a single-digit improvement in CPU usage may scale to hundreds or thousands of CPUs in aggregate. So we have the responsibility and the privilege to work on small problems that make a big impact. So that brought us to our vision here. We wanted to be able to easily and specifically identify the performance impact of an incoming pull request. So it's important that the process should be easy because otherwise developers will simply not do it or skip that step. We wanted to have specific information about performance as well. Our existing tools were not precise enough to confidently narrow down what was causing a change in resource usage or a change in CPU usage. Certainly not to the level of specific lines of code. And finally, we wanted to apply this process at the level of a pull request, as that's our typical unit of code change. So the question was how? We had a few existing ways of trying to enhance performance, among other things. The first is code review. Most of you probably have some sort of code review process, and ideally, code review can be a place to get some performance feedback, especially if a reviewer can spot the difference between a function that's in constant time versus linear or quadratic time. That kind of thing can sometimes be caught in code review. If you know or suspect that the code you're reviewing is in the hot path, that might be your first line of defense in saying, we know that this needs to be efficient. However, it can be difficult to predict how complex systems will interact, and there are many situations where non-obvious problems can have performance penalties. We also run end-to-end test. We don't routinely monitor the end-to-end tests for performance or how long they take to execute, but we can tell if something is off. So there's timeouts and such that can be triggered if something slows down a lot. However, this is also imprecise, and there's already some variability in these end-to-end tests. They can make it difficult to separate the signal from the noise in identifying performance issues. We also observe our binaries in production. We have alerts to notify us when CPU or memory usage spikes beyond predetermined thresholds. However, these alerts can be noisy, and a spike in consumption may or may not have anything to do with the binary we ship. Different usage patterns can affect the resource consumption in ways that are difficult to predict and alert on. And that higher usage can happen organically. For instance, if everyone in a region started scraping twice as many metrics, we would notice that the usage, the resource consumption, had increased, but it would take some digging to figure out exactly why and what was happening. In the end, we would determine that it was a change, but not a problem. And finally, we have an existing benchmarking solution. For us, that's PromBench, which is a tool in the Prometheus ecosystem, which had been set up by our intern the previous summer. So that did provide some consistent feedback on how our changes would perform. However, it did not tell us what was causing the difference. So I'll share an example to illustrate. So yeah, it doesn't look like you can see this all that well. But this is an example of part of a dashboard of the benchmarking that we can run. It shows there are differences between two versions, but it can be hard to tell exactly what those differences are. And sometimes it's hard to tell what's real too. For instance, the upper left graph shows CPU usage of two different versions, but the lines cross each other regularly, and they don't have a consistent pattern. So a lot of the times they're kind of close together. And it appears that the blue line is maybe a little bit worse, but it's hard to know what's happening and what the difference is. And it's even harder to tell if that difference is meaningful or significant. Is that actually going to affect our overall performance across the fleet? This led us to consider a more precise tool. So where benchmarking measures overall performance, profiling allows you to do a deep dive into your performance. Profiling allows you to analyze the code typically at the level of a function call. And in this way, you can identify specifically where an application is resource hungry. It's maybe helpful to think of this as profiling is like a stopwatch and benchmarking is like a microscope. The profiling tells you how long, and the benchmarking, the benchmarking tells you how long, and the profiling allows you to zoom in on specific areas of the code. So Go has had profiling baked into the toolchain since the early days of the language. Some of you may be familiar with pprof tool. Just by a quick show of hands, how many people have ever used pprof? Okay, quite a few people, yeah. So profiling is valuable for learning about the performance characteristics of your program. A typical use case for this kind of profiling might be running a test or a test suite with the profiler attached, and then reviewing a chart, like the one on the right side of the slide, that provides feedback on where the program consumes CPU or memory during the execution of that test or test suite. So you can pass like the -mem profile and -cpu profiles flags to go test or to go run to profile your program, and it writes out files of profiling data. And you can visualize that data. However, it is ultimately a snapshot. So what is continuous profiling? Well, it's like profiling, but continuous. It really is almost that simple. So instead of collecting profiling data over a set execution of a test or a test suite or maybe your actual application, the profiler runs continuously, collecting data on an ongoing basis. This typically means that the sampling rate can be slower because the monitoring is a long-running process where you'll get all the data that you need eventually. The continuous profilers that we evaluated each have various visualizations that they support for exploring the data that they collect as it is collected. So you might see something like this graph. So Google's been doing this for a while. In 2010, Google published a paper on how the company uses continuous profiling internally. And it's been a valuable tool for many years, but it's taken a long time to get that to our public-facing services. So it wasn't until 2018 that Stackdriver Profiler, which would become Cloud Profiler, was launched. And even now, how many people are familiar with Cloud Profiler or a similar tool? Yeah, barely anyone. So for continuous profiling, we may start to see something like this. So it's going to have familiar graphs of CPU or memory usage. And then in the lower part of the screen, you'll see that there's a what Parker calls an icicle graph that breaks it down basically through your entire call stack. So with that, you can zoom into specific function calls. This has a help window that's popped up that shows you exactly where the line of code that it's analyzing is. And you can really drill down into those specific parts of the program. So for instance, if I select this lex function from the Prometheus code base, you can see the entire call stack on the right side, and you can see what else that function is calling underneath it on the icicle graph. And from there, you literally can jump into lines of code. You can see that this next function is taking up about half the time of the lex function. So it sends you specifically to those lines of code that you're looking at when you're drilling down into the graph. There's two main mechanisms for collecting profiling data with Go. One is using the traditional pprof endpoints. There's built-in support in Go, and that integrates with the testing frameworks, as I mentioned. However, it does require you to instrument your code. You have to import the pprof package, and depending on your use case, you may have some significant overhead involved in doing that. Some of the newer solutions are based on eBPF, which I will not attempt to explain right now, but it hooks directly into the kernel, and it may end up having lower overhead overall. It's also not language dependent. So any compiled language is going to mostly work out of the box. And then more and more interpreted languages are being supported as well. So the downside of eBPF, of course, is that you need to be able to hook into the kernel. And so you'll need permissions to do that. So with that, I'm going to jump into how we designed our continuous profiling solution. We're going to talk about 4 of the key decisions that we made of how to handle this. So we'll start with the profiling tool. I'd love to say that we evaluated every profiling solution on the market and picked the very best one on technical merits. But the truth is our decision ended up being a little bit simpler than that. We were aware of 3 continuous profiling tools that seemed relevant to us that had some significant momentum behind them. So those were Parka, the Google Cloud Profiler, and Pyroscope. Pyroscope was actually the merger of 2 open source projects that got acquired by Grafana. And they lean into the flame graph kind of language, Pyroscope, fire, all of that. So they're very cutely themed around fire. Whereas Parka, it has icicle graphs, which go down instead of up. They're basically the same thing other than that. Yeah, Parka was designed with Prometheus conventions in mind. And so it was a familiar space for us as people who work on Prometheus. And then finally, I'll mention Google Cloud Profiler as well. This definitely would have been a natural choice for us as people who work on Google Cloud. It required basically no setup for us. However, it didn't have a cute themed name, and so we ruled it out. Just kidding. We considered that we have customers that are not on Google Cloud. And so we run our own CI on GitHub. We're like more in the open source world than we are in the Google world on our team. And so we were wary about locking ourselves into a Google Cloud specific solution. So ultimately we decided to work with Parka. So the next question that we had to figure out in our design was where to test. So you can run like a micro benchmark. You can profile over some sort of predetermined run of the program, or you can collect continuous profiling data in production. So with a micro benchmark, it has the advantage that it's a controlled environment. You can compare your tests easily side by side. However, it's not ideal for like real world scenarios. You don't know if something different is happening in production than is happening in your tests. So as another benefit though of the micro benchmark side, you have a faster feedback loop. You don't have to actually deploy new versions to production to give your feedback. So you can run your benchmark and in a matter of minutes, you can start to see feedback on how your change is doing. In production, you do capture your actual usage patterns and bottlenecks, and you may be able to identify issues that don't appear in testing. There could be a customer or someone out there that's running your binary that's doing something strange that's not covered by your benchmarking tests. However, with deploying to production, there are some additional technical and non-technical challenges that I'll get to a little bit later that are worth considering. In a perfect world where you have unlimited time and resources, you can combine both as well to get the best understanding of your performance in a testing environment as well as in production. So our next decision was how to integrate the continuous profiler. And we ultimately decided on a GitHub command. So we have a /prombench command that you put in a GitHub comment that aligns with our PR workflow. That makes it very easy for our developers to initiate the profiling, and it keeps the performance analysis closely tied to the code changes. So thinking back to the vision, this is at the level of a pull request, we're able to do some analysis. So a quick summary, in the final design, we trigger the profiling with a GitHub command. We have a set of tests that are run in prombench to simulate load. We went with the micro benchmarking and not the production benchmarking to start. Parka, the chosen tool, provides a visualization system for comparing and viewing profiles, and then resources are cleaned up after profiling. So some lessons learned. Some of you might be familiar with this quote. The first 90% of the code takes the first 90% of the development time, and the remaining 10% of the code accounts for the other 90% of development time. If only we had that other 90% of our development time, we could have done a lot more. Unfortunately, time is scarce. So although we all have some limits on the amount of time that we can spend on a project, those limitations came sharply into focus for a summer intern. with only 3 months, if an approval process took 4 to 6 weeks, it was just a non-starter for us. Even a single week delay could be costly if it didn't yield positive results. Something like rolling out a new feature that collects user data to the entire fleet for GCP would be expected to take some time. And so that was one of our key constraints in trying to profile in production. For our situation, even introducing a new binary into production, like a continuous profiling tool, Parka, requires a significant process where we have to review all of the code and get it approved through legal and all of that. And so we really decided to focus in on the areas where we could be more nimble and make a quick impact. In general, it seems like the bigger the ambitions, the more delays you need to plan for. And we just didn't have a lot of delays in our budget for a summer intern. The positive side of these time constraints, of course, was that we were able to complete some focused work and deliver on a timeline, a short timeline, to get real positive results. Next, we benefited from prior work in the Prometheus project itself. So we run a fork of Prometheus, and they already had a benchmarking tool that was ready for us to use. And they had already integrated some continuous profiling. And so we were able to take advantage of a lot of their work to get this set up. We also had expertise nearby, as the person who implemented the continuous profiling solution for the Prometheus project is on our team and was available to our intern as he was working on this project. Finally, just a word about profile-guided optimization. So in a world where everything works as intended, you can feed your profiling data directly back into the Go compiler, and it will improve the performance of your final binary. The data is kind of used to coach the compiler on which compiler-level performance optimizations make sense. And so it's sort of like how an athlete's coach may be able to focus on the athlete's areas of greatest need. However, in our case, we did not find any discernible difference between the binary compiled with the profile-guided optimization or without. It's not entirely clear why, but it could be that with the Prometheus project in general, there's already been a lot of optimization, and so people have found some of the lower-hanging fruit, and the profile-guided optimization itself couldn't find any better optimizations. So that's certainly one possibility. I'm sure there are other things that could be happening as well, but we didn't see any immediate payoff, and so we kind of walked away from that fairly quickly. Additionally, profile-guided optimization would be expected to have the best payoff if you're collecting production data, so that you're optimizing for production and not for your test cases. So there could be differences there that would have impacted it. Next, Google Cloud is a very large organization, and concerns about software licensing are important to us. So the least restrictive licenses make it easy for us to adopt certain software, while more restrictive licenses can be difficult. So in our case, we did have a licensing issue where we would have had to go through a lengthy approval process to use one of the profiling tools that we considered, and that did end up being a limiting factor for us. So a few key issues about profiling in production. So although the overhead of a sampling profiler should be expected to be pretty low, it does cost some overhead, and different people may or may not be okay with the overhead. A proponent would likely argue that the performance improvements that you can get by being able to analyze your code and make improvements that are targeted to where your application is spending the most time will pay off, and that you'll get that performance back through those improvements. Another potential concern is leaking sensitive data through profiling data. So there's labels attached to the profiling data that could contain sensitive information. And there would definitely need to be safeguards in place to prevent leaking anything that you don't want to get to that platform. And finally, there's complexity involved in aggregating large amounts of profiling data. So as far as I know, most of the current public profiling solutions are not really built to work on the scale of thousands of clusters. So this is kind of a different problem than most people approach with a profiler. So some ideas for future work. One thing that we plan to do is to expand profiling to multiple binaries. So within our project, we focused on our hot paths and specifically our fork of the Prometheus binary, where we were able to look at the single component of our solution that has the most resource consumption. However, we could easily expand this to include other binaries within our solution. We can profile our operator, we can profile other components like the rule evaluator. We could also implement profiling in production. I imagine it would work something like this. Our users would opt in to sharing their profiling data. That would go to our profiling data aggregation service. And then we could store that data in some sort of public data so that the developers that are working on our open source project would have access to that and know where to target within the program if they're looking to make optimizations. The aggregator service would have to do a few things. It would have to sanitize the data. It would have to sample it to reduce the volume of the data so that you don't get an overwhelming amount of data. So like just as a side note, like when we're collecting profiling data, we can easily get like gigabytes of data within a couple days just sampling a single binary. So you do have to kind of narrow that down unless you want to store all of that forever. And then finally, yeah, being able to store some of that data and retain it in a bucket. So I don't know when or if we'll get to building this, but I hope that we can put it on our roadmap eventually. However, we have some unanswered questions. So the first one is, does production profiling data really make a difference? It's possible that the benchmarks are good enough and that there's not significant differences in usage patterns between the test and production, or that the differences don't matter because they lead to the same optimizations. So until we start collecting more production profiling data, we really don't know what that looks like. We don't really know if there's any interest in publicly available profiling data from the producers or the consumers. So that is to say, are people willing to share profiling data? And are there people out there that are interested in having access to profiling data so that they can see beyond whatever instances they're running themselves, how these applications are performing? And finally, profiling is a game of diminishing returns. That is to say, the more you use profiling data to optimize your application, the harder it will be to continue to find new areas to optimize, and the lower the expected return on each improvement. At some point, theoretically, the easiest and most valuable thing you can do to optimize for efficiency is to remove the profiler entirely, because the profiler itself will cause more overhead than you can improve by using it. So I'll wrap up with a few predictions. So first, I think that continuous profiling is an emerging best practice for applications with sufficient scale or performance requirements. Continuous profiling is certainly not appropriate for certain kinds of applications. For instance, you wouldn't really want to invest in continuous profiling for toy applications or short-lived jobs or even workloads that aren't performance sensitive. Even when performance is important, it's often not the most important thing. For instance, a lot of the startups that I've worked at are very feature-driven, and the cost of inefficiencies is a cost that you pay so that you can continue to deliver new features. However, if you're working in something like an online retail business, for instance, you may be interested in efficiency because you know that milliseconds of delay can sometimes influence whether you keep a customer on your site. So there may be cases where that's helpful. But as Google has found with its billion plus user services, profiling can be implemented on a very large scale with very low overhead and provide valuable insight. I think that large open source projects will eventually figure out a way to collect some profiling data from production. This is kind of a different model than a lot of startups and individual companies, where if you're running your own binaries and you're the only person running them, then you have all of the data that you need. However, with large open source projects like Prometheus, like something like Kubernetes, like some of these other big projects, you don't know exactly how it's performing on other people's machines. You may just be shipping software and hoping for the best. But I think that it makes sense to integrate some sort of profiling data along with the other kinds of telemetry that we see out in the world already. Then my final prediction is a little bit more ambitious. I predict that everyone in this room will try continuous profiling in the next year. So if you're saying to yourself that you don't think you will, why not? With some of the tools that are available on the market now, it's easier than ever to get started. Our intern was able to accomplish it in 12 weeks in an environment that puts up some barriers to acting quickly. I'll say it that way. But it can be a very valuable and powerful tool to have at your disposal. And I hope that sharing our experience has inspired you to give it a try. If you want to connect with me, you can find me on GitHub or on Blue Sky. And if you have thoughts about anything I've presented, please reach out. I'll be here the rest of the day. Thanks.
Thank you, Adam. Well, we are actually going to roll right into our next talk, which is given remotely. So Mariah's going to set it up here, and we're going to roll into that. And then you can see Adam around and ask him any questions. So thank you so much.
Hello everyone at GoWest Conference. My name is Ulysses, and welcome to using TinyGo and LoRa to monitor and control a hot tub. I apologize I can't be there in person as I'm currently on vacation at Disneyland, which is a great place to be with my family. Hello everyone at GoWest Conference. My name is Ulysses, and welcome to using TinyGo and LoRa to monitor and control a hot tub. I apologize I can't be there. there in person, as I'm currently on vacation at Disneyland, which is a great place to be with my family. Just a few agenda items about the things that we'll go over today. First of all, we're going to kind of go over the reason why this project even started to begin with. We'll talk about some hot tub internals, maybe a lot more things that you guys wanted to know about how hot tubs work, and some things that I wish I would have known.
And go full screen.
Hello, everyone at GoWest Conference.
Oh yeah, you
It's always easier knowing after the fact. Next, we're going to talk about what is LoRa as a way to communicate versus Wi-Fi and Bluetooth, which we'll get into that a little bit more. But LoRa is a great low-power technology that is much better at communicating long distances. Then we're going to go over the RP.
Probably because we have the array lights off.
P2040, which is a microcontroller that is a very useful and very inexpensive microcontroller for you to play with. And then we're going to talk about TinyGo. TinyGo is a great way to get some Go programs onto microcontrollers such as the Raspberry Pi 2040. Next, we're going to I'll give a little high-level design overview of kind of what we are going to go over. And then we're going to talk about how, reverse engineering a serial protocol, even though it looks easy, it's actually a lot harder than it seems. Then next, we'll kind of wrap it all
Right.
up with a lesson
Looks like
learned,
we are
and then
having
we'll
some
talk
technical
about
difficulties
what's
with the
next.
audio.
So just a little bit
So
about
we are
myself.
going to
I'm
roll
a tenured
into
gopher
lunch. If you
that's
can bring
been
up the lunch
using
slide.
Go for 10
So
years, I guess.
there's lunch set up right
2014.
outside the
Crazy. I
doors,
got to
and then
attend one of
for
the-
dietary
I got to
requests,
attend
they're
the
on the
first
table
Go
at the
conference,
end.
which is
So please leave those unless you
fantastic,
requested
and
them
got to
specifically.
meet
So we
a
will
lot of
roll
fun
into
gophers
that.
along
Thank
the
you.
way. One of those fun gophers that I got to meet was Ron Evans. He created, him and the hybrid group created some really cool libraries called GoBot, GoCV, and now TinyGo, which are great things for doing embedded systems programming, which the crazy part is, if you guys remember,
This is going there. I don't even know where this sounds. What are you doing? Yeah. So this should be on output. I mean, I'm getting sound to the stream. I'm just not getting sound to the room. I don't know where. Yeah, I don't know why I'm not getting it sound. I'm not saying. No, I'm saying I can see it.
for that keynote speech, Rob Peck basically said, yeah, this isn't built for embedded systems. And Ron's like, we're going to change that. So here we are. Another fun thing that I love doing is in my spare time is to fly remote control airplanes. So I like to fly planes. These are not electric. These are gasoline powered planes that run on regular 87 or I guess 91, grade gasoline. A lot of fun and a lot of, gives me a lot of fun things to tinker with. Next, I also got into thermal safety. This is a lot of the motivation for this. You guys will see that. decided we're gonna get a 3D printer. We're gonna have fun, and my kids love it. So they use the thing more than I do, which is a lot of fun. And then lastly, I spend some time, about 2 times a week. I spend up helping out as a planning commissioner for my city. So that's just a little bit about myself. Let's talk about how this thing all started. And kind of how I already alluded to you guys that, yeah, like COVID was definitely a fun time. For us as a family with 4 children, it really, really was hard having to homeschool kids and having to, you know, keep ourselves sane when we couldn't go out anywhere. It was kind of hard. So we kind of decided, what's one of the fun things we love about vacation? It's a pool. Well, the problem is in Utah, you can't really have a pool because it's so cold and it's only good for about, 3 or 4 months of the year. So we decided, let's get a hot tub because the kids are going to have fun with that. So I did some basic research, did some digging around and kind of settled in on a hot tub that, I thought, hey, it's built with, industry standard components for the hot tub internals, and this should be good to go, right? I think, let's buy this one. The one caveat there was that, when the salesperson talked to us, they did say, if you want to get one that has Wi-Fi control, we'll need to upgrade you. So that's going to be an extra $600. And my wife and I looked at each other and we're like, yeah, do we really want that? Is that really that important? And I said, you know what? I'll just get that installed later. Not a big deal, right? I can program. I got this. So fast forward to about 3 or 4 months ago, I started to realize like, hey, we need to get some Wi-Fi controls on this thing. Electricity prices are definitely not cheap when you run a hot tub always at hot all the time. So, and always having to remember like, oh, turn down the temperature before we go to bed, right? Like these are things that you kind of start appreciating the Wi-Fi features of the hot tub. And that's kind of when it's like, okay, maybe it's time to look into this. Let's see. This shouldn't be that bad, right? Like this should be like a $100 module. Get this on Amazon, and we'll get this going. Not a big deal, right? So little did I know that we're gonna dive into a little fun trip of what actually happened. So cracked open the hot tub and looked inside, and oh, it looks like here it is. Here's the part. Or here's the control that I have. Now let me go on eBay to see if I can find it. I couldn't find any single Wi-Fi controllers for this thing. I'm like, are you kidding me? Like this is crazy. Not a single thing. So then at that same time when I was doing some Google searches for this Wi-Fi controller, I found this really cool project. It's basically the work of a bunch of folks that created a GitHub project to reverse engineer the protocol of this Balboa spa controller, and I thought, great, this is all I need. Like, once I have this, I should be good to go, and this shouldn't be that crazy. So we're going to kind of pause in our little journey, and next we're going to kind of jump into talking about LoRa, and kind of, why, I decided to go with LoRa. So what is LoRa? So LoRa actually stands for long range. It's actually just that, long range. And so basically it's very long range communications. Think about Bluetooth, think about Wi-Fi, right? Wi-Fi is pretty good. It has good range, but not the greatest range, right? Like if you're like me, you probably have a few range extenders in your home if you need that to get good Wi-Fi coverage. So yeah, Wi-Fi is okay, but not that great. And Bluetooth, while it's easy to get stuff out, it does not have super great range. And it uses, and yeah, it has its uses, but for this, not so much. So what makes this project a good choice for using LoRa? Well, number one is LoRa is great for things that are not very high bandwidth. So for example, sending things like temperature or command, little turn on the pump, turn off the pump. That's not super high bandwidth. So that's one thing. Next part is there's a lot of Wi-Fi interference. So if you look at a hot tub, it's this huge case, right? You've got this big enclosure that's kind of low to the ground, and then you're trying to hopefully get a signal from that to your device inside your home, right? Either your smartphone or your mobile phone or some other device. And that gets kind of hard with things like Wi-Fi or Bluetooth, just from the enclosure, just from getting through enough walls in your house. It's kind of a problem. So this is where LoRa is great, because it has such great range that you can pick it up in an urban setting like your home. The other thing that's also really nice about LoRa is the fact that it also runs in a whole separate frequency band than your common Bluetooth and or Wi-Fi signals, which is great. So that's another plus. The last thing that I wanted to talk about with LoRa is that it has incredible range. So if you have clear line of sight, you can get about 2 kilometers, which is pretty far. And then there's also other uses that I've seen where people can run LoRa on a button cell coin battery for about a good 10 years, which is incredible. So those are kind of the pluses, right? In summary, long range, low power, and just you're on a whole different frequency band from everybody else, so a lot less interference. So let's talk. So that was LoRa. That was kind of how I want to talk to the hot tub, right? Great. Next, I want to talk about what microcontroller do you want to use. There's a lot of microcontrollers out there. You'll see so many of them. They have a lot of different features. You can get like an Arduino Uno. You can get the RP2040. There's also a Raspberry Pi that you could use for this, which is a little overkill for this, but it's still an option, right? So there's a lot of options, but I ended up choosing the Raspberry Pi 2040 just because it's such a cheap platform. It has a lot of devices and peripherals, and it's very easy to develop for. The one huge plus also that made me choose the RP2040 is the fact that it has support for compilation in TinyGo, which makes it really, really easy to write a Go program and get it burnt onto the board. So the RP2040 is the name of the microcontroller, but however, you're going to want to get a board on that controller. So what I ended up using was the Adafruit Featherwing, and it's kind of in the picture over here. You'll see that. It's nice because it allows you to have USB. You can actually put a battery on there if you wanted to. It's got a lot of really nice peripherals. Great way to go, and super cheap. So if you're working on a microcontroller project that you'd like to kind of experiment and play around with, the Featherwing from Adafruit is actually a great way to go. All right, TinyGo. So whenever you hear people talking about microcontrollers or embedded systems programming, you'll hear people talk about Arduino, right? Which, yes, Arduino is great, and they have huge library supports for many devices, and you'll see great tutorials online from Adafruit or other vendors. Fantastic. But we're here at Go at a Go conference, and so we're going to talk about some other tools that we have at our disposal to do embedded programming. But yeah, like how would you do that, right? I mean, we can use Go today to compile to ARM or Intel or any other microprocessor. But what if you're trying to target something like a microcontroller? How do you do that? So here's where we enter TinyGo. So TinyGo is a compiler that basically compiles Go to even the smallest of places. For example, like a microcontroller. The cool thing about TinyGo is it's not just microcontrollers, but the new hotness of WASM now is something that you can actually do with TinyGo. There's just a lot of cool targets that TinyGo can compile to, and so it's a really cool project. Thanks to Ron Evans and the countless contributors. There's so many of them. I know I've personally met a bunch of the contributors for GoBot, GoCV, TinyGo, and they're fantastic people. TinyGo is such a great project, and it's basically all possible because of all of their efforts. The one thing with TinyGo is it's not hard to use. You just have to get yourself into the mindset that it's a compiler, right? You're now using a new compiler to target some platform. So the cool thing with TinyGo is that there's number one is you can compile your Go program to a microcontroller for example, in this example, the RP2040, and then there's also some driver code that you can include that you can talk to devices, like you can talk to let's say like a sensor, a temperature sensor, or a light sensor, and a lot of that code is already pre-baked into those driver libraries, which is great. And then if you want to see what other microcontrollers are supported by TinyGo, they have a great list here that I've referenced in the slides. So definitely check it out. Go see what's supported, and yeah, just I think the biggest thing with TinyGo is try it out. And the other thing is remember that you're also not using a full Go, right? Like TinyGo supports most of Go's features, but where you are running in a constrained area and space, that's going to be your limitation. So just remember that when you're developing that, yeah, you're not going to be probably doing a lot of concurrency, although there is some support for it. You're talking about a microcontroller, so just remember that. And the TinyGo project goes over the specifics of what they do and don't support. All right, so just as a quick aside here, so this is kind of my ideal version of what this would look like if we're gonna do this. So we have on the left here, we have a hot tub, right? We have the hot tub controller, and according to that awesome GitHub repo that I found, it looks like that hot tub controller talks via RS-485. Now RS-485 is basically a serial communication protocol that's used by a lot of industrial control devices, kind of like if like what RS-232, that's kind of like a UART. If you guys have seen that, like a terminal, that is the equivalent of what RS-485 versus RS-232. It's kind of like that, but just in a different format, built around industrial and automation devices. So that's that part, right? So we need something to convert those signals from the hot tub controller into something that we understand. So there's an RS-485 controller, and then the next part would be we have the Raspberry Pi 2040. That's our microcontroller that would then interact with that RS-485, and then at the end here we would have this RFM9X LoRa radio. This is the one I ended up using, but there are definitely other models and or makes of LoRa radios out there. That's the one I settled on. It's a great little radio, and then so that would be on the hot tub. So inside the hot tub would be kind of all this hardware here that would kind of sit there and transmit and receive signals. On the other end, you could have a Raspberry Pi 0W, which is the wireless version of the Raspberry Pi, with this same radio receiving signal. So this is, this is a proposed or my first cut at doing this and kind of what I was thinking of at the time. The reason why I went with the Pi 0W versus the RPi 2040 is that we do need to have a bridge. So either, we have, we're receiving these LoRa signals, we do something with them, and maybe we want to send them to Home Assistant, right? Or maybe we want to send them somewhere else, right? So that's kind of why I ended up going with the Raspberry Pi Zero, and just for the Wi-Fi communication part of it. All right, next we're gonna go over kind of at a high level how I was thinking about how this software would work. So at the very top here, we'd have some basic, some logic that we would need to write to, get the signals from the RS485 chip, do some reading and writing from that, and then this middle piece here, that's kind of like the key component, right? Is we would need to have some logic there to decode the protocol that the spot is using. So this is the secret sauce. This is where where we encode, decode the signals coming in and out of the spa. Then I was thinking, so for example, my spa has lighting controls that actually has some LED lights that you can turn on, which is kind of fun. And then the temperature control, which is the main part of what I wanted to do. There are other things, like there are pumps that circulate the water and jets and things like that. I didn't want to get too involved with that, so we just kept it as a temperature sensor. And then Ulysses, and welcome to using TinyGo and LoRa to monitor and control a hot tub. I apologize I can't be there in person as I'm currently on vacation at Disneyland, which is a great place to be with my family. Just a few agenda items about the things that we'll go over today. First of all, we're going to kind of go over the reason why this project even started to begin with. We'll talk about some hot tub internals, maybe a lot more things that you guys wanted to know about how hot tubs work, and some next. Then we're going to go over the RP2040, which is a microcontroller that is a very useful and very inexpensive microcontroller for you to play with. And then we're going to talk about TinyGo. TinyGo is a great way to get some Go programs onto microcontrollers such as the Raspberry Pi 2040. Next, we're going to I'll give a high level design overview of kind of what we are going to go over. And then we're going to talk about how, reverse engineering a serial protocol even though it looks easy, it's actually a lot harder than it seems. Then next, we'll kind of wrap it all up. And now TinyGo, which are a great thing. Ron's like, we're gonna change that. So here we are. Um, Another fun thing that I love doing is in my spare time is to fly remote control airplanes. So I like to fly planes. These are not electric. These are gasoline powered planes that run on regular 87 or I guess 91, grade gasoline. A lot of fun and a lot of, gives me a lot of fun things to tinker with. Next, I also got into 3D printing. This is a lot of this, the motivations for this, you guys will see that COVID was definitely some fun times. We, as a family, we decided we're going to get a 3D printer, we're going to have fun, and my kids love it. So they use the thing more than I do, which is a lot of fun. And then lastly, I spend some time, about 2 times a week, I spend up helping out as a planning commissioner for my city. So that's just a little bit about myself. Let's talk about how this thing all started. And kind of how I already alluded to you guys